Welcome! Today we're going to look at parametrization and line integrals. Consider the scalar equation of the line L, which is y equals a half x plus 3. And so have a look at this. Here's a diagram of that. We've got a slope 1/2. It intercepts the y-axis at the point 0,3. So here's our y-axis. Here's our x-axis, and here's the line. So since we have slope 1/2, the vector 1, 1/2 is parallel to the line. But let's take a little look at this. So if I just go across from some given point on the line, 1, and then how much do I have to rise up to come back to the line? Well, remember, slope is rise over run. So the rise would be 1/2 if I run 1. Okay, now viewed in terms of a vector, I go in the I direction, or I hat direction, 1, and in the j hat direction, 1/2. And so I can view that as the vector v is 1, 1/2. So I go 1 unit to the right and 1/2 units up. So here I've got a vector v that's parallel to the line. Now there's another way to write this. We could call this pulling out the 1/2, factorizing it out. It's 1/2 of the vector 2, 1. So 2, 1 is parallel to the line. Okay, fantastic. So what does that tell us then? Well, that gives us a vector equation of this line, really, because if I take a vector from the origin 0, 0 to any given point on the line, say P, okay, let's draw an arrow from the origin to P. Okay, so this is the vector OP, which is in here. And then from P, what if I travel in the direction of the vector V, or 2, 1? So now let's travel some multiple of that. So T times 2, 1. That's a vector parallel to the line. And suppose that multiple takes us here. Okay, and so then this takes us to another vector. If we just add this vector plus this vector, remember how vector addition works. And so this is the vector R. But since it's from the origin to a point on the line, it also gives us a point on the line. Now, what we want to do is find an arbitrary point on this line. And so here I've chosen x is equal to -4. So let's take a look at this. 1/2 of -4 plus 3. Well, that's -2 plus 3 is equal to 1. So we have a point, -4, 1, is on the line L. Okay, something like this, -4, 1, and I happen to have put it in roughly that place on the diagram, which is great. Okay, now this point, the point from O to here, let's call that point R, uppercase R, and then we have the vector lowercase r is the vector OR. And so remember, in terms of positions, This is given by r minus o. And since o is just 0, 0, this gives us a point x comma y on the line. Okay, now putting this together, so r is equal to p, or OP. So let's go OR is equal to OP plus t times 2, 1. So this is a vector equation. This is a vector, this is a vector, and this is a vector. But since OR is just r minus o, which is x comma y, if r is equal to x comma y, so we have x comma y is equal to p plus t times 2 comma 1. And this gives us a description of points on that line, right? Now if p is equal to minus 4, 1, well then we get exactly this, right? And so it describes points on a line, but it's also a vector equation. So now if we want to describe a segment of this line, we can allow t to be between some bounds, say between 0 and 1, for example. And if it were between 0 and 1, we would start at p, and we would finish at minus 4, 1 plus 2, 1. Okay, so that's a simple understanding of parametrization of lines and how we get line segments in parameterized form. So now we can also put this together, expand this and add components, and so we would get the description of the point x comma y as 2t minus 4 comma t plus 1. Okay, now if we think about this from the other point of view, so suppose we have the parametrized form of this line, can we go back and get this equation? Well, yes, and it's pretty easy. I'll show you how. So suppose we have this description and we want to go back to an xy description of the point. So we would write x is equal to 2t minus 4 and y is equal to t plus 1. And what we want to do is eliminate t from these equations so that we get a relationship between x and y. So from this equation right here, we can write t is equal to y minus 1. And then wherever we see a t in here, we can replace it with y minus 1. So doing that, we've got x is equal to 2 times t, which is 2 times y minus 1, and subtract 1, and then we can expand this and get 2y minus 6. And so rearranging that, well, we get 2y is equal to x plus 6, and then we divide throughout by 2, and we get y equal to a half x plus 3. So pretty straightforward, especially when it comes to lines. So parametrizations are useful in calculating line integrals, and so you've seen an example of a line integral earlier when we briefly considered flux. However, they can also be useful in the study of integers. All right, now what we have been looking at or will look at are called real parametrizations, because we're taking t to be a real number between some bound and some upper bound. Okay, but there's also a rational parametrization of various objects, but not all objects. So a circle, for example. Now if I take a circle here of radius 1, and talk about some arbitrary point, well, a real parametrization of this circle would be cos t comma sine t, because this point is described by the cosine of t. All right, so for example, all right, now t being the angle in that case, so t is the angle there. So this over this is the x coordinate over 1 being cosine t. We have cos of t for the x-coordinate because it's adjacent on hypotenuse, but that hypotenuse is 1. Now similarly, the y-coordinate, this little piece, is this, well, the sine of t is the y-coordinate over the hypotenuse, which is 1. So we have y is equal to sine of t, opposite on a hypotenuse. And so that's a real parametrization of the unit circle. But there's also a rational one given by this, but I'll show you how to think about getting that. Now here, you take t to be any rational number. If you sub in a rational number there, you have a rational point on the unit circle. So you construct this geometrically. So again, I'll just draw a circle of radius 1. Okay, and then since it has radius 1, we always have, well, there's only one curve, right? So we have this point, 1, 0. Okay, now I can take a line that passes through 1, 0 of slope t. And provided that t is not infinite, this line of rational slope will intersect this circle again in another point. And then I can get the description of that point by subbing the equation for this line into the unit circle. And this is what I get. So magically, if I sub in any rational number t into this, I get a rational point on the unit circle. So why is that interesting? Well, because if you look at it and call z that denominator, so letting lowercase x be uppercase x on z and lowercase y be uppercase y on z, right, then x squared plus y squared equals 1 gives you uppercase x squared plus uppercase y squared equals z squared. And so this actually gives you Pythagorean triples. For example, 3, 4, 5 is produced from the parameter t equals 2. So this tells you then, since there are infinitely many integers t, then there are infinitely many Pythagorean triples. Triples of integers satisfying a squared plus b squared equals c squared. So let me just show you here. If I just take t squared minus 1 2t and then t squared plus 1, and then I just make a list of these choosing t over integers, I get a list of Pythagorean triples. Right, so some of these are not very interesting because they have a 0 coordinate. But we've got 3, 4, 5, 8, 6, 10, 15, 8, 17. And you can think of that as 8, 15, 17 if you like, and so on. So in this way we can get infinitely many Pythagorean triples, which I think is fairly interesting. All right, let's move on. Parametrization of curves. So from now on, we're going to consider real parametrizations of curves. Find a parametrization of the curve y equals x squared. Well, what you want to do is represent the y in terms of the letter x and then just change the name of it. So y equals x squared, so a description of points on this curve is x comma x squared. And now we can say, well, let t be our parameter. Let that just be x in this case. So we just have t comma t squared. where t is any real number. T is an element of the set of real numbers. Okay, now consider the parametrization x comma y is t plus 2t squared. Find the scalar equation of the curve and then sketch curved arrows showing the curved segment from t equals minus 2 to t equals 2. Well, it's already here, right? But let's go through some of the details here. So what we have here is t equals x minus 2. And so what we do is, so we've just got x is equal to t plus 2. So we're just taking the 2 over to the other side and writing this. And then we have y equals t squared, but since we have an expression for t that we got from this, then we can just sub that in, and so that gives us x minus 2 squared. Right, so that is a parabola. Y is least when x is equal to minus 2. So here we've got a point minus 2, 0. But that corresponds to when t is equal to 0. Okay, now when t is equal to minus 2, if I sub that into this, I get 0, 4. So the point 0, 4 happens when t is equal to minus 2. Now if t is equal to 2, subbing in 2 here, we'd have 2 plus 2 is 4. 2 squared is 4, so this is the 0.44, which happens when t is equal to plus 2. Okay, so have we answered that question? The curve there is sketched. What about the arrows on the curve, right? So obviously, if you're thinking about t as if it were time, then minus 2 is before 2, and so the arrows here are going left to right. Okay, but you can work this out in another way. So note that, okay, so let's think in terms of the vector r. So take an arbitrary t value, and then this here is the vector r of t from the origin O, 0, 0, to this point, say r. Okay, now what about r dash? So r dash of t is equal to, well, just taking this and differentiating, we have 1 comma 2t. Okay, so at this point t is roughly minus 1, so that would be r dash of minus 1 equals 1 comma minus 2. So going over 1 and down 2. So we have r dash is something like this. So r dash is parallel to the curve at a given point t. Okay, so also looking at this, the x component here is positive. So x dash of t equals 1, which is positive. So that tells you x is increasing. Which tells you that the arrows go left to right as t increases. Now the y component, so y dash of t is 2t, and that depends on the sign. Depends on the sign of t, right? So if it's positive on this side, the arrows are going up. And if it's on this side, so if t is negative, so over here t is negative, the arrows go down. Okay, another example. So we can get some exotic examples of parameterized curve. Here's a cycloid. X comma y is r times t minus sine t, comma r 1 minus cos t. So this gives a cycloid. And I might have, yeah, so some more pictures here. No, I don't have that one. But I can easily represent that here too, right? I would write parametric plot for that. And I would just type this in and press a button. All right, let's move on to the next page. Parametrizations of three-dimensional objects. To parameterize a surface, now surfaces are written usually in terms of x, y, and z. For example, the sphere, unit sphere is x squared plus y squared plus z squared equals 1. But the beauty of a parametrization is you can reduce 3 letters to 2 letters in a description of the points. So a parametrization of the unit sphere is sine t cos u, sine t sine u, cos t. All right, so this gives you a description of all of the points on the unit sphere in terms of only 2 chosen letters. So if you choose two real numbers, t and u, plug them into this description, well, it gives you a point on the unit sphere. Okay. Now another example, the surface x comma y comma z given in parametric form, cos t plus u, t squared u, t minus u, with t between minus 2 and 2 and u between minus 2 and 2. This is shown in this figure below. So if you want to have a better view of this, something like this. So you can see that we have a surface here in 3D, and it's produced just from these 2 letters t and u. So for example, and you could do this by hand, right? If you chose a real number t and a real number u, plug it into this on your pocket calculator, you would get a point, right? And you could sketch that point in 3D. So, you know, to build up a picture like this, you'd have to do that a lot of times. Okay, now we can also parameterize curves in 3D as well. So take this, for example. XYZ is sine t, cos t, 1 on 10 times t. Now, x is sine t here, and y is cos t. So taking x squared plus y squared, we have sine squared t plus cos squared t. And we know from trig identities that that's 1. All right, so looking down on this equation from above, we should have x squared plus y squared equals 1. Okay, now taking the fact that z is equal to 1/10 t, and then multiplying both sides by 10 so that t is equal to 10z. But here's t inside the sine function. That's x. So x is equal to sine of t, which is sine of 10z. Okay, so now we have a relationship between z and x. That's just a sine wave. Right, so from one point of view, we have a sine wave, and then looking from above down, we have a circle of radius 1. Okay, so what does this look like in 3D? Well, it is a helix. Okay, and so let's think about this. So looking down, it looks like a unit circle. Something like that, and then in terms of x and z, we have a sine wave of a particular frequency. Okay, so something like this. And then there's also a wave in terms of z and y. All right, but let's navigate around this thing because I have it right here. All right, so first of all, ignore the red and the black for now. So here I've got the helix, right, plotted in 3D. So if I take this, drag it, and look at it from above, well, you can see it looks like a circle, right? So that's this, what I have here on the left. And now if I put that back, okay, and now I take it, turn it this way. Not so easy to do here. Okay, so you're starting to see what looks like a sine wave. You've got to orientate it just right so you see a sine wave. All right, so the projection of this onto the xz axis will be a sine wave. Okay, and then if you do it the other way, you'll probably get a cos wave. So look at it from this side. You get a cos wave. It starts up at the top, comes down. Okay, so now let's talk about the red and black arrows. Put this back. Okay, so remember, we also have a vector description of this parametric curve, and it is the vector from the origin to a given point r on there. Now as I change the parameter t, I'm changing that vector. You see, the vector's from the origin to a point on that, so that is r. Now what's the little black thing? Well, that's an arrow. That is r dash. Or actually, I've got some multiple of r dash. So it is tangent to the curve at that point where the arrow ends. I mean, it doesn't quite look like it, but I've designed it so it's supposed to be anyway. All right, so as we go around, that black arrow should be tangent to the point that we're following, and tangent to the curve at the point that we're following. It's supposed to be anyway. All right, and so that is r dash, that little black segment. Okay, so let's sketch this here on our page. Let's just put the point here, and then so the origin, let's find it. It's got to be, I don't know, about there. Okay, so sketching this. We've got the vector r of t, and then I think this is pointing up. Should be pointing uphill. So this arrow here, or vector, is r dash of t, the derivative of this vector. Two very important things. Okay, let's look at example 6.3. Derivatives of parametrized curves. Calculate dy on dx for the parametric equations of the curve given by this. Okay, so dx on dt, just differentiating that with respect to t, well, we've got 2t. And then dy on dt, well, differentiating this with respect to t, we have 8t minus 20t cubed. Okay, so now dy on dx is dx on dt, or sorry, dy on dt over dx on dt. And so that is so 8t minus 20t cubed over 2t. And so now we can divide the t into the numerator and cancel a t. So we have 4 minus 10t squared. Okay, now can we relate this to x again? Well, that looks easy in this case because t squared is x minus 8. So this is 4 minus t times x minus 8 squared. Oh, no. Just x minus 8, no square, because t squared is x minus 8. Okay, so if we expand this, then we have minus 10x, and then 4 plus 80 is 84. So 84 minus 10x, and that's dy on dx. So from the parametric representation, we can easily get dy on dx in terms of t and in terms of x. Okay, so let's just do another calculation to confirm this. And I suppose we'll put that in this little box. So since there's squares in here, we can get an equation for y in terms of x easily. So we have y is equal to 4 times t squared, which is 8x minus 8. And then minus 5 times x minus 8 squared, because t squared is t to the 4th is t squared squared. Okay, so that gives us a quadratic equation. So now if we expand this, we're going to get minus 5 x squared plus 84x, and then minus 352, I think. I'll just double check this here. Okay, yes, and I'll put this where you can see it. Minus 5x squared plus 84x minus 352. All right, so looking at this, we can easily take dy on dx, or y dash of x is minus 10x plus 84, agreeing with this. Okay, let's go on to line integrals. If f of xy is defined on a smooth curve C in 2 space, the line integral of f along C is defined by this, right? So notice we have a subscript of C, the integral of f of xy over the curve C ds. So let's talk about what this means. This is the area under the surface, not the volume under the surface. It's the area under the surface, z equals f of xy, along the curve C. So for example, now I've got a little bit of width here, but I mean the area under this, right? The area of this side piece. Now here, in this example, down the bottom is our curve C, but it happens to be linear in this case, right? So hence, you know, maybe the term line curve, or sorry, line integral. But it doesn't have to be a line. So here's an example on the right where the curve at the bottom is curved, not linear. Nevertheless, this is called a line integral. So this is C down the bottom, that curve. Okay, and what does this represent? This represents the area of this side piece along here. So the surface area under that surface. So here we might have a surface over the top, but this is a slice along this curve C under the surface, and that calculation gives you the area of this, I don't know, think of it as a ribbon or something, right? Surface area of that slice. Okay, line integrals have many applications, including the what does it say? Including the calculation. Let's change that, of the arc length L of a curve C, where this is given by the line integral, L is equal to the integral of 1 ds over the curve C. It's easy to calculate this arc length when we first parameterize the curve C. Let R of t be a parametrization of the curve C using parameter t. Consider figure 48. So that's on the next page. Okay, there we go. So here's our curve C. Here's R of t, this vector. And here is R of t plus delta t. And then this is delta S. Okay, figure 48. The vector R dash of t is a vector tangent to the curve C at t. Now remember this, I've shown you plenty of examples of this. So if we're looking at this, in this helix, R dash of t is this little black vector that is parallel to the curve at the point P, or point R maybe, okay? So R dash of t is a vector tangent to the curve C at t. So we make the substitution, ds goes to the norm of R dash of t dt. Okay, but what's going on here is, so delta S over delta t is approximately the norm of R dash of t. And so we put exactly ds on dt is the norm of R dash of t. And so we get this substitution. dt. Okay, so this is the substitution that we make in these line integrals here and here, if we have a parametrization of x and y. Okay, so let's have a look at theorem 15. Let R of t be a parametrization of the curve C using parameter t. The arc length L of the curve C from t equals a to t equals b is given by L equals the integral of 1 ds over the curve C. And I wonder if I have a picture of this here so you can look at it. Not quite. Okay. And now making this substitution, ds goes to the norm of R dash dt. So we have this now, which is from t equals a to t equals b. And now consider what this is. That's the square root of x dash of t squared plus y dash of t squared dt. Okay, and if you wanted to, you could even factorize out an x dash out of this. So when you did that, you would have x dash of t square root 1 plus dy on dx all squared, and then dt. Okay, so this is another formula for the arc length of a curve, right? But then, so this is dx because this is dx on dt, and so we can make the dt's go away. So we can write this as the integral of 1 plus dy on dx squared dx. Right, but now you have to change these values. Find out what the x equals. Okay, So this is what you would have learned in a one variable calculus course. You would have learned this formula for the arc length. Okay, but here we've got a very simpler formula for it. This is a line integral. Okay, so back to the idea of the surface area of the ribbon under the surface. So the arc length of the unit circle is the length around this, right? But we can also view this in the light of it being a line integral, because we've got a surface z equals 1, you know, that's the top of this. And then the curve is x squared plus y squared equals 1. That's around the bottom here. So that's C down here, all the way around. And so in this interpretation, as a line integral, the surface area of this ribbon around here is the arc length times 1, which is just the arc length. So that's why it gives you the arc length, because the height here is 1, so it's 1 times the arc length. So the area coincides with the arc length when you use z equals 1. All right, so what have we got here? So let's calculate this. So taking the first derivative, we've got r dash of t is minus sine t cos of t. Okay, now if we take the norm of this, we have minus sine t all squared, but we're taking a square root as well. So minus sine of t all squared, and then plus cos of t squared. And so this is the square root of sine squared t plus cos squared t, which is the square root of 1, and that's 1. Okay, well that makes this line integral, easy. So we've got the integral over c, which is from t equals 0 to t equals 2 pi radians, right? So 2 pi radians takes you all the way around this. Okay, and so that's 1 r dash of t norm dt. So that's the integral from 0 to 2 pi of 1 dt, since that norm is equal to 1. Right, and this is just t from 0 to 2 pi. So 2 pi minus 0, which is 2 pi. Okay, so that gives us the arc length around the circle, or circumference of the circle of radius 1. Remember that circumference of the circle is 2 pi r, but here r is equal to 1. So this is a circumference of the circle, 2 pi in the case that the radius is equal to 1.